Hello, this is Brett from SurvivalComms. Today we have a legacy piece of test equipment I picked up at the Orlando Hamcation this year for just a few dollars on our bench. This is a Model 920 standard deviation meter produced by Measurements, which was a division of the McGraw-Edison Company. Now, Measurements McGraw-Edison produced test equipment in the 50s and 60s. The manual I found for this particular meter was printed in 1970 by the Measurements division of Automated Industrial Electronics of Batesburg, South Carolina, so this was produced before 1970 as far as I know. This device measures the deviation of frequency modulated RF signals between 25 megahertz and 1 gigahertz. You can also use it to check distortion and for the presence of noise on an FM RF carrier. So what is deviation? The Cliff's Notes for what concerns us today is that deviation is how much space a frequency modulated RF signal occupies when modulated. RF spectrum is like real estate, and that being the case, good fences make good neighbors. In the image we're looking at here, we are seeing a 25 kilohertz span of spectrum and our unmodulated carrier. Now in this image here, we have modulated our carrier with a 1 kilohertz tone, and you can see just how much more space our signal occupies. Our equipment setup to use this device is as shown here. The device we are testing is a VHF Motorola portable radio. At the left, we have an audio signal generator set to generate a 1 kilohertz tone at 80 millivolts, which is the frequency and level specified in the service manual for this radio's measurement. The audio signal is injected into the microphone port of our device under test. The RF connector of the radio is connected to a T featuring a minus 30 dB sample port, and it's terminated into a 50 ohm load. The standard deviation meter is connected to the sample port, and the specified deviation for our device under test is 4.3 to 4.6 kilohertz for a 25 kilohertz channel. When we activate our PTT, the radio delivers a signal sample to the input of our meter for measurement. Here's a more conventional arrangement here. I've got my service monitor. Here's our device under test, and the RF feeds in the service monitor here. This is the audio. The audio is a 1 kilohertz tone modulated at 80 millivolts RMS, and it's being fed into my test box. My test box is connected to our device under test, and we manipulate the push to talk just like that. Now that we have seen the test performed on a more modern piece of test equipment, we have a value to use as a control for our testing of the Model 920 standard deviation meter. The average deviation is 4.23 kilohertz, shown at the top in the oval. In the circle at the bottom is the deviation measured on both sides of the carrier, which is where we derive our average from. This shows that there is a slight imbalance in deviation in our device under test, but I'm not going to sweat that. Now let us discuss the instrument and how it works a bit before we do our testing of it. You'll note that the items that we're discussing at the time in the images will be highlighted in yellow. The first is the power switch, and this is simply a slider switch that controls the power to the instrument. The meter either will work off of an internal rechargeable battery pack, which fortunately was not left in our instrument, or with its own built-in AC power supply. And here in this image of the back, you can see our input for our AC power supply, and also the switch that allows us to select from the internal battery, recharging the internal battery, or the AC power supply. This connection is our RF signal input, which is a BNC female connector. The input is limited to 200 milliwatts, so don't make the mistake of direct connection to a transmitter. Our meter also included an antenna for off-air testing in the near field as well. This is our RF gain control, and this provides approximately 26 dB of attenuation, but again, do not make the mistake of considering this to be a suitable load for a transmitter. This is the controls for our local oscillator that makes the magic happen in conjunction with the mixer. Tuning range is 25 to 50 megahertz with a coarse and fine tuning adjustment. On the inside front cover of our instrument, under the 8 ohm speaker, is a chart spelling out the harmonic relationship tuning of the instrument to provide its coverage between 25 megahertz and 1 gigahertz. Sensitivity is 25 millivolts at 25 megahertz, dropping over its tuning range to 50 millivolts at 500 megahertz, and then decreasing as anticipated from there. The instrument features a local speaker jack and volume control for de-emphasized audio, and the cover has an 8-ohm speaker and plug for it. Additionally, there is a scope jack for monitoring of non-de-emphasized audio. The peak reading meter measures battery, allows for tuning the local oscillator and gain control, and has ranges of 20 kilohertz, 6 kilohertz, and 2 kilohertz for deviation measurement. The other two settings are for checking the discriminator and the gain of the audio amp. And lastly is a switch at the top of the instrument that allows us to select whether we want to measure the deviation before the carrier or after the carrier. Now that we understand the instrument, its controls, and the configuration of the device under test, we can go ahead and perform our test. We're going to check a portable radio on a 25 kilohertz channel, 146 megahertz in frequency. We go ahead and connect our instrument, or connect our device under test to the instrument, turn our power on. We turn our RF gain fully counterclockwise. We take our audio level, center it, plug in our speaker. Take our switch up here for our meter and place it in the tune position. We know for our local oscillator that the frequency we desire is 146 megahertz, and we look on our harmonic chart on the door and we see that's going to reside between 35 and 40 megahertz. So now that we've got all this stuff set up, we go ahead and transmit, and we find our signal. And we look to peak it. Turn our RF gain up a bit, see if we can get more of a peak here. Back our RF gain down. Tuning it in the blue zone. Now to perform our test, we place our meter in the 6 kilohertz position and perform our test. And we can see that our deviation is just under 4.25 kilohertz, which is pretty much what our service monitor told us. So although this piece of equipment is dated, it's still providing good service, and it's reasonably accurate considering that it hasn't been calibrated since 1993. And it just goes again to prove that the real action at Hamcation is outside, not inside the main building. I hope this helps. This is Brett from SurvivalComms. Till next time.